The idea that matter consists of smaller particles and that there exists a limited number of sorts of primary, smallest particles in nature has existed in natural philosophy since time immemorial. Notably, modern physics no longer deems elementary particles indestructible. Even elementary particles can decay or collide destructively. They can cease to exist and create particles in result. Increasingly small particles have been discovered and researched. They include molecules, which are constructed of atoms, that in turn consist of subatomic particles, namely atomic nuclei and electrons. Many more types of subatomic particles have been found. Most such particles were eventually found to be composed of even smaller particles such as quarks. Particle physics studies these smallest particles and their behavior under high energies, whereas nuclear physics studies atomic nuclei and their constituents, protons and neutrons. Early development. The idea that all matter is composed of elementary particles dates to at least the 6th century BC. The philosophical doctrine of atomism and the nature of elementary particles were studied by ancient Greek philosophers such as Leucippus, Democritus, and Epicurus, ancient Indian philosophers such as Kanada, Dignaga, and Dharmakirti, Muslim scientists such as Ibn al-Haytham, Ibn Sina, and Muhammad al-Ghazali, and in early modern Europe by physicists such as Pierre Gassendi, Robert Boyle, and Isaac Newton. The particle theory of light was also proposed by Ibn al-Haytham, Ibn Sina, Gassendi, and Newton. Those early ideas were founded through abstract, philosophical reasoning rather than experimentation and empirical observation, and represented only one line of thought among many. In contrast, certain ideas of Gottfried Wilhelm Leibniz contradict to almost everything known in modern physics. In the 19th century, John Dalton, through his work on stoichiometry, concluded that each element of nature was composed of a single, unique type of particle. Dalton and his contemporaries believed those were the fundamental particles of nature and thus named them atoms, after the Greek word atomos, meaning indivisible or uncut, from atoms to nucleons. First subatomic particles, however, near the end of 19th century, physicists discovered that Dalton's atoms are not, in fact, the fundamental particles of nature, but conglomerates of even smaller particles. Electron was discovered between 1879 and 1897 in works of William Crookes, Arthur Schuster, J. Thomson, and other physicists. Its charge was carefully measured by Robert Andrews Millikan and Harvey Fletcher in their oil drop experiment of 1909. Physicists theorized that negatively charged electrons are a constituent part of atoms, along with some positively charged substance. And it was later confirmed. Electron became the first elementary, truly fundamental particle discovered. Studies of the radioactivity, that soon revealed the phenomenon of radioactive decay, provided another argument against considering chemical elements as fundamental nature's elements. Despite these discoveries, the term atom stuck to Dalton's atoms and now denotes the smallest particle of a chemical element, not something really indivisible. Researching particles interaction, early 20th century physicists knew only two fundamental forces, electromagnetism and gravitation, where the latter could not explain the structure of atoms. So, it was obvious to assume that unknown positively charged substance attracts electrons by Coulomb force. In 1909, Ernest Rutherford and Thomas Royds demonstrated that an alpha particle combines with two electrons and forms a helium atom. In modern terms, alpha particles are doubly ionized helium atoms. Speculation about the structure of atoms was severely constrained by Rutherford's 1907 gold foil experiment, showing that the atom is mainly empty space, with almost all its mass concentrated in a tiny atomic nucleus. Inside the atom. By 1914, experiments by Ernest Rutherford, Henry Moseley, James Franck and Gustav Hertz had largely established the structure of an atom as a dense nucleus of positive charge surrounded by lower mass electrons. These discoveries shed a light to the nature of radioactive decay and other forms of transmutation of elements, as well as of elements themselves. It appeared that atomic number is nothing else than electric charge of the atomic nucleus of a particular atom. Chemical transformations, governed by electromagnetic interactions, do not change nuclei. That's why elements are chemically indestructible. But where the nucleus changes its charge or mass, the atom can become the one of another element. Special relativity explained how the mass defect is related to the energy produced or consumed in reactions. The branch of physics that studies transformations and the structure of nuclei is now called nuclear physics, contrasted to atomic physics that studies the structure and properties of atoms, ignoring most nuclear aspects. The development in the nascent quantum physics, such as Bohr model, led to the understanding of chemistry in terms of the arrangement of electrons in the mostly empty volume of atoms. In 1918, Rutherford confirmed that the hydrogen nucleus was a particle with a positive charge, which he named the proton. By then, Frederick Soddy's researchers of radioactive elements, and experiments of J. Thomson and F.W. Aston conclusively demonstrated existence of isotopes, whose nuclei have different masses in spite of identical atomic numbers. It prompted Rutherford to conjecture that all nuclei other than hydrogen contain chargeless particles, which he named the neutron. Evidence is that atomic nuclei consist of some smaller particles. It became obvious that, while protons repulse each other electrostatically, nucleons attract each other by some new force. It culminated in proofs of nuclear fission in 1939 by Lise Meitner, and nuclear fusion by Hans Bethe in that same year. Those discoveries gave rise to an active industry of generating one atom from another, even rendering possible the transmutation of lead into gold, and those same discoveries also led to the development of nuclear weapons. Revelations of quantum mechanics. Further understanding of atomic and nuclear structures became impossible without improving the knowledge about the essence of particles. Experiments and improved theories gradually revealed that there is no fundamental difference between particles and waves. For example, electromagnetic waves were reformulated in terms of particles called photons. It also revealed that physical objects do not change their parameters, such as total energy, position, and momentum, as continuous functions of time, as it was thought of in classical physics. See atomic electron transition, for example. Another crucial discovery was identical particles, or, more generally, quantum particle statistics. It was established that all electrons are identical, although two or more electrons can exist simultaneously that have different parameters, but they do not keep separate, distinguishable histories. This also applies to protons, neutrons, and to photons as well. It suggested that there is a limited number of sorts of smallest particles in the universe. The spin statistics theorem established that any particle in our space-time may be either a boson or a fermion. It was later found that all fundamental bosons transmit forces, like the photon that transmits light. Some of non-fundamental bosons also may transmit forces, although non-fundamental ones. Fermions are particles, like electrons and nucleons, and generally comprise the matter. Note that any subatomic or atomic particle composed of even total number of fermions is a boson. So a boson is not necessarily a force transmitter and perfectly can be an ordinary material particle. The spin is the quantity that distinguishes bosons and fermions. Practically it appears as an intrinsic angular momentum of a particle, that is unrelated to its motion but is linked with some other features like a magnetic dipole. Theoretically it is explained from different types representations of symmetry groups, namely tensor representations for bosons with their integer spins, and spin-or representations for fermions with their half-integer spins. This culminated in the formulation of ideas of a quantum field theory. The first of these theories, quantum electrodynamics, allowed to explain thoroughly the structure of atoms, including the periodic table and atomic spectra. Ideas of quantum mechanics and quantum field theory were applied to nuclear physics too. For example, alpha decay was explained as a quantum tunneling through nuclear potential. Nucleons. Fermionic statistics explained the nucleon pairing, and Hideki Yukawa proposed certain virtual particles as an explanation of the nuclear force. Inventory. Modern nuclear physics. Development of nuclear models made prediction of properties of nuclides possible. No existing model of nucleon-nucleon interaction can analytically compute something more complex than 4He based on principles of quantum mechanics, though. The most developed branch of nuclear physics in 1940s was studies related to nuclear fission due to its military significance. The main focus of fission-related problems is interaction of atomic nuclei with neutrons, a process that occurs in a fission bomb and a nuclear fission reactor. It gradually drifted away from the rest of subatomic physics and virtually became the nuclear engineering. First synthesized transuranium elements were also obtained in this context, through neutron capture and subsequent beta-decay. The elements beyond fermium cannot be produced in this way. To make a nuclide with more than 100 protons per nucleus, one has to use an inventory and methods of particle physics, namely to accelerate and collide atomic nuclei. Production of progressively heavier synthetic elements continued into 21st century as a branch of nuclear physics, but only for scientific purposes. The third important stream in nuclear physics are researches related to nuclear fusion. This is related to thermonuclear weapons, as well as to astrophysical researches, such as stellar nuclear synthesis and Big Bang nucleosynthesis.